Hello, my name is Reed Miller. This is lab number 5, magnetic braking with Faraday. The purpose of this lab is to collect data of a magnet falling through a tube of aluminum foil, model that data computationally on GlowScript, and then compare the model with our observed data. The physics we're going to be using is Faraday's law, which relates changing magnetic field and area of a surface to flux, and then we can calculate EMF and current through there. The Boutz-Savart law for magnetic field through a ring, and then derivative of flux with respect to time, which gives us the EMF of the tube around the falling magnet. Main results we got from this lab is that the model on GlowScript predicted the time for the magnet to fall through the entire length of the tube to be 1.117 seconds, and our experimental data was 1.252 seconds. So some assumptions we make is that air resistance is negligible. The bar magnet acts as a magnetic dipole as it falls through the tube, and the foil acts as just a conducting tube around the magnet. The system is the foil and the bar magnet, and the surroundings will be everything else. For the experiment details, we have initial conditions where the foil of aluminum is held above the ground vertically, and the bar magnet is held above the top of the tube with the north pole facing downwards. For procedure, we're going to use the magnetometer app to locate the north pole, mark that pole with an N, and then like initial conditions say, hold the tube vertically and the magnet above the tube. Position a smartphone to video and capture the entire length of the tube in frame, and then start recording, and then drop the magnet through the tube, rewatch the video, and determine the timestamps of when the magnet enters and leaves the tube to determine how long it takes to fall through the tube, and repeat for 5 times. So here's the data I got from the 5 trials, getting an average time of 1.252 seconds, and then the measurements I took of the tube length, radius of the link, magnet mass, and mu of the magnet from lab 3. So here's my GlowScript code to model the experiment. In step 1, the first part, we're just inserting our measurements of the aluminum tube, the radius, length, and width. Step 1, second part, we're doing the measurements of the magnet, so the mass and the mu of the magnet. In step 2, we're going to use the dipole function we created in lab 3 to model the magnetic field of the bar magnet. So there's the code for that. In step 3, we're going to calculate the magnetic flux. This is the biggest part of the code because as the magnet falls, the change in magnetic field creates a change in flux. So this is the code to calculate the change in flux. In step 4, we're going to use that code, the change in flux, to calculate the current that is induced in the aluminum foil. Since as the magnet falls, the change in flux induces an EMF in the coil around it, and the EMF creates a current. So by dividing the flux by the resistance, change of flux by the resistance in the foil, we get the ring current starting in step 4. In steps 5 and 6, we calculate the B field at each ring in the aluminum foil. So we assume the aluminum foil is made up of an infinite amount of rings, that we can calculate the magnetic field at each one of those rings. There's the code for that, and then we can use that to calculate the magnetic force from the rings on the magnet. And in step 7, we calculate the gravitational force on the magnet, which is just mass times gravity, and then summing those force of gravity and magnetic force up on the magnet, we get a net force on the magnet in step 7, second part. In step 8, we change the magnet's velocity and position by applying Newton's second law, and there's the code for that. So here is the model. The gray 2 represents the aluminum foil, with the blue at the bottom representing the current, and there's the velocity versus time graph for our model. It gave us, an experimental time of 1.117 seconds. So some sources of error for this lab is that the tube was not held exactly vertically or perpendicular to the surface of the earth. The method of calculating time in the experiment was not very exact using the smartphone. There's also air resistance involved. And what if the resistivity of the conductor were reduced as close as possible to 0? How the dynamics of falling magnet change? If the resistance was reduced to 0, that means the forces pulling the magnet up would increase as the current would also increase. And these forces would increase until the magnet basically stops in air when the forces are equal to the gravitational force pulling downwards. What if the holes or slots were cut into the tube? How would this affect the ring current in your model? The holes would disrupt the current flowing through the foil, thus decreasing the magnetic force up, and the magnet would fall through the tube faster, since the gravitational force would be greater than the magnetic force. And that is all. Thank you.